So, hello everyone. I'm Beth Kimani, the AIML track lead at Google Developer Groups, Chuka University. And our today's topic, we shall try to understand the age of anatomy through deep learning. So, um, and we shall try to move further from the traditional feature engineering into deep learning, where we study neural network bases and also the feed-forward architecture. So, yeah, we shall look into the introduction, then the neural network basics, then the forward architecture, and the training, and then we shall do a conclusion. Today we won't have hands-on, but we will do it in the next session. So, yeah, let's go uh, into it. So, we all live in a world where artificial intelligence has become the new buzzword to describe everything from a simple set thermostat to a self-driving car. But today we are peeling back the marketing layer to look at the architectural engine driving the revolution deep learning. So if you look at the history of computing, for 60 years, we followed the logic-based approach where we told a computer, so if X happens, do Y. And and this works for calculators, and but it fails for a human. And how we write and how do we write an if then statement for the say smell of roses or the feeling of sunset? You really can't. And so deep learning has changed this paradigm, and it is just a subset of machine learning. And uh, sorry. So instead of giving computers the rule, we gave it the brain-like structure and a million examples. And we stopped being programmers, and from then we started being educators. We started training computers. So, but what is it really? If you if you come across the word deep learning, what comes in mind? So, at its simplest, deep learning is a subset of machine learning, and it uses artificial neural networks with multiple layers, and hence the word deep. And it has to represent the abstract increasingly data. And today we are going to walk through the architecture of that thought process. So, um, okay, to understand deep learning better, um, just give me a second. So, so I'm sure if you have in the past been a biology student, you have come across the human brain, and in the human brain, you were able to learn about neurons. So we're going to look at a neuron and the structure of a neuron. So you're just going to look at one, say this one. So from here you can see we have the neuron, and we have the dendrites, we have the soma, we have the nucleus, we have the myelin sheath, we have the axon, and we have the Schwann cells, and we have the nerve endings. So this is basically the same idea we use for the neural networks. So for the neural networks, we have dendrites which receive input signal. So these dendrites, they receive the signals, and then we have the soma, which is the cell body, and it just sums up the signals. And then we have the axon, which transmits the output signal, and then we have the synapse, which is a point of connection where weights are applied. So basically, that's it. Um, it's basically the human brain translated into computer uh, language. So yeah. So Okay, so to understand it, I'll give you a little history on it. So in the 1950s, we have uh, uh, we have computer scientists uh, who was called Frank Roosevelt. Roosevelt, and what he did, he looked into the biological neuron, and he tried to digitize it. And the biological neuron receives signals, and if those signals are strong enough, it fires, right? And our artificial version does the exact same thing mathematically. So imagine you're deciding whether to go to a concert tonight, and your neuron takes three inputs. So, is the weather good? So that is the first input, and then the second input is the ticket cheap, and also if is your favorite band playing. That's the third input. But all inputs are equal. If your favorite band is playing, then you might go even if it's raining. So this importance is what we call the weight. So um, I'll try to explain it this way. So this is what we call the weight. So the importance of each feature, and we multiply the input by the weight. So we do an input multiplied by the weight, and then we add the bias. So the B is our bias. So the bias is your personal threshold for saying yes. So if you're a hermit, then your bias will be very low, and you need a lot of convincing to leave the house, right? And if you're an extrovert, your bias is very high. So yeah, so we just did the weight multiplied by the input, and then we add the bias. So, and then finally we pass the sum through the activation function, and this is the on or off switch. So in modern deep learning, we use the um, rectified linear unit, or the RU, the ReLU. Just a second. We use the rectified linear unit, uh, which basically says if the signal is negative, then ignore it, and if it is positive, pass it through, right? So this simple nonlinearity is what allows the network to learn complex patterns rather than just simple straight lines. Interesting, right? Um, um, that's some good thing. So we shall try to look at the feed forward network, and now imagine one neuron can't do much, right? That's so obvious. But if we have a stack of millions of them together to get the feedward architecture, um, if you put a million of them, you get what is called the feedward architecture. And picture a wall of light bulbs arranged in layers. Okay, so the input layer is the first wall. Okay, if you're looking for if you're looking at a 28 by 28 pixel image of a handwritten number, you have 784 input neurons, and one is always for each pixel, right? And one is for each pixel's brightness. So the hidden layers, let me just see if, yeah. So we have the hidden layers, and this is where the magic happens actually. And data flows from the input through these layers. And in the first hidden layer, neurons might fire when you see, say, the horizontal line. And in the second, they might fire when they see, say, a circle. And by the time we reach the final hidden layer, the network has assembled all lines and circles into a concept, right? So the output layer just produces the final prediction. So it is the final verdict, and um it has like 10 neurons. So for digits 0 to 9, and the one that grows the brightest is the network guess. So yes, so this is called feed forward. Um, this is called the feed forward because information flows in one direction. So it is input, hidden, output, and there are no loops. It's horizontal, one line. It is massive. It is multidimensional, and it is a massive multidimensional assembly line where the data is refined at every station. So that's just what we have looked at here. So yeah, uh, let's try to look at training the network. So this is where we get to like check the dense, fully connected layers, and it is one of the most crucial parts in our roadmap. Um, and how does the network actually learn, right? I'm sure you're all asking yourselves how this happens. So we first build a network, and the weights are totally random, and it's essentially a blank slate that guesses randomly. So to train it, we need three things, and we need let me just see. Um, yeah, we need the loss functions, we need the mean squared error, and we also need the cross entropy. So we shall look in depth about this, so don't worry. So we'll start with the loss function, and it is the grade, and it's abbreviated by the J theta, and it measures how far the network prediction is from the actual ground truth. So uh, we show the network a picture of a 4, and it guesses a 7, right? So the loss function measures exactly how wrong the guess was. So that is it. And it gives a single number. It gives us a single number, and that single number is the error. And our goal is to make that number a 0. So we also do have some back propagation, and that is the blame game. So the back propagation is more of the heartbeat of deep learning. So once we have the error, remember we have the error, and let me just see if it's in my slide. Yes, actually we have it. So once we have the propagation, once we have the error, uh, at the end, we go backward through the network using the chain rule, and the chain rule from calculus, and it just helps us to calculate the gradient of the loss with respect to every weight in the network, and uh, we calculate how much an individual weight contributed to what wrong answer, right? It is like a manager looking at a failed project and then tracing the mistake to specific employees in specific departments, right? Yeah, and then we do have the gradient descent. Let me see if I have it. Yeah, I have it. We do have the gradient descent, and the gradient descent is our correction. So now we have to fix the mistake. So imagine you're standing in a foggy mountain, right? So, and let's classify that as our high loss. And you want to go to the valley, which is the low loss, right? And you can't see the valley because it's foggy, but you can feel the slope of the ground under your feet, right? So you take small steps in the direction that goes downwards, and that step size is the learning rate. So if the step is too big, you might overstep the valley. So if the step is too small, you might take millions of years to get there. So we repeat this process: forward pass, calculate loss, back propagation, update weights. So thousands or millions of times until the network converges to the truth. So yeah, basically that's it. That's the backbone of deep learning. And uh, just sum it up. What we've discussed today isn't magic. It's the symphony of linear algebra and calculus. So we've started with neurons and what weight inputs, and then we have arranged into forward architecture and that exact features. So the forward architecture is just what exact features, and then we use training. So that is the feedback loop loss, back propagation, and the gradient descent to fine tune those weights. And then the results, it's a machine that can translate languages in real time. So it has a diagnosis. So maybe to diagnose a disease from X-ray, which are better than humans, or even to generate art from a single prompt. So as you live today, remember deep learning isn't about coding. An answer is about building a structure that is capable of discovering the answer for itself. So we're no longer just writing programs, we are building the foundation for the new kind of digital intelligence. So thank you. Next time we shall try to go deeper into deep learning. So until then, bye bye. Bye.